Hello, everybody. It's my great pleasure to welcome you on the 26th EURADOS webinar. And this webinar will be about EURADOS experiments in a proton therapy facility with a gantry which is mounted, with a synchrocyclotron which is mounted on the gantry. But before we'll start webinar, I would like to those of you who don't know EURADOS, I would like to say a few words about our organization. So just one moment because my slides are not changing. Can you just confirm that you see slide oh yes, now slide number 2 is there. So EURADOS is a non-profit organization which is working in radio protection and dosimetry. And the aim of our work is a radio protection both of individuals and environmental, radiation monitoring, radiobiology, but also radiation monitoring and dosimetry in medical applications. As you can see on the map, we have more than 80 members institutions, and we are gathering more than 600 individual members, so scientists, who are working in 9 working groups. And those working groups are covering the aims of EURADOS. And today's webinar is organized jointly by Working Group 9, Radiation Dosimetry in Radiotherapy, which I have a pleasure of being a leader, and by Working Group 11, so High Energy Radiation Fields, where Marco Carezana is a leader. You can see here the link to EURADOS webpage. We are a very open organization, so if you like our topics and if you like the area of our research, please feel free to contact us. So today's webinar, we will have 4 presentations, which will cover different aspects of the experiment, which was performed in 2019 in a Mastro clinic in Maastricht. If you have questions, please ask them in the chat. We will answer them after all presentations. And just to mention that our webinar is recorded, and later on you can also see it on YouTube, our YouTube channel. And over there you can see not only this webinar, but also all previous webinars and our winter schools and our general assemblies. So if you're interested in EURADOS, feel free to see to have a look on our YouTube. So the first speaker today will be Gloria from Mastro Clinic in Maastricht. Gloria is a medical physicist who is working in proton radiotherapy with a long experience in treatment patients, but also with an interest in out-of-field dosimetry. So Gloria, the screen is yours.
Hi, Liliana. Thank you so much for the introduction. Okay. Now you should see my presentation in presentation mode.
Yes.
Yes. Okay. So yeah, I will introduce you a little bit, which are the main characteristics of our proton facility in Maastricht. And yeah, I would like to thank EURADOS for coming in 2019 for performing all these measurements, and you will see today the results. So just to give you a little bit of context, we are in the Netherlands, in Maastricht, and in the Netherlands there are about more than 20 photon clinics, and it has been granted by the government 4 permits to build proton therapy centers, but there are actually 3 built, and there is the first one is in Groningen. It started clinical activity in January 2018. The second one is in Delft, in Holland PTC, and it started activity in September 2018. And we are here in the south, and we started in February 2019. Over the years, there has been the trend of making the proton accelerators smaller and smaller. And one way of doing that is by using superconducting magnets, and this allows a more compact design and a reduced weight of the accelerator. So this is the IBA, the Varian, the IBA Synchrocyclotron, the Proteus one, and this is our system, the Mevion Synchrocyclotron. And so if we look in the Netherlands and in Belgium, we have one center of each type. And so the one in Groningen is a Proteus Plus and is the same as in Trento and is similar to the one in Krakow. I mentioned this one because these are the centers where the EURADOS measurements were previously performed, and my colleagues will show you data on them, and they will compare our results with them. And so this is a layout of, we are a radiotherapy department, and we have external beam therapy and brachytherapy. And this was the previous situation. So we had 8 bunkers, and 4 of them were occupied by Linux, by TrueBeam, and 1 brachytherapy. And what they did is, in order to build the Proton Center, they moved some Linux, and also in 1.5 photon bunkers, they built our Proton facility. And why they could do that is because the diameter of the accelerator is very small, only 1.8 meters and only 15 tons. So the superconducting synchrocyclotron is directly mounted in the gantry, as you can see by the arrows in these pictures. And our facility is like a 3-story building. So the central part is the treatment room, this where the patient stays, and just below and above is where the outer gantry rotates. So this is the space required for the gantry to go up, and here is the space required for the gantry to go down. And so the Mevion S250i system consists of a double-sided concentric gantry. Here you can see in a schematic view. So in blue is depicted the outer gantry, and so it's this one. And in the outer gantry, there is the accelerator, as I mentioned, and also the scanning magnet. And then in the inner gantry, that they can rotate independently, and once we are ready to deliver the beam, they are both aligned with an angle position accuracy within 0.1 degrees. And in the inner gantry, depicted in green, there are the beam monitors and the extendable nozzle. In the extendable nozzle, there is the range modulator system and the adaptive aperture. And the scanning magnet, the beam monitors, and the elements of the extendable nozzle compose the dose delivery system. Now let's focus on the scanning magnet. So the scanning magnet is the last element of the outer gantry, and is a single focus scanning magnet. So it's this one, and our irradiation field is a square because of this type of a scanning magnet. I mentioned this because typically the proton accelerators consist of two magnets. A first magnet in the horizontal scanning for the deflection in the horizontal plane, and for the deflection on the vertical plane, there is a second magnet located with some distance in between, and this makes a rectangular irradiation field. But in our case, it's a single focus, and we have a square field, 20 by 20 centimeter. Now the beam monitor. So the beam monitors is the first element of the inner gantry. So here you can see, so this is the end, this is the outer gantry, and this is the inner gantry, is the first element. And one of the particularities is that the beam monitors only see the pristine proton beam energy. And this is something different compared to other commercial systems. And then let's focus on the first element of the extendable nozzle. So the first element is the range modulator system, and it is composed by 18 Lexan plates of different thicknesses. And with this combination of plates, we can create 161 energies with an energy step of 2.1 millimeter, and we can cover from the surface, so 13.5 MeV as the minimum energy to 2 to 7 MeV, that we can cover a range in water of 32 centimeters. And it has a very fast energy change of about 50 milliseconds. And then the other element, the last element of the nozzle and of the whole beam line is the adaptive aperture or MLC. There is an MLC, and this is because our beam from the vacuum window to the isocenter travels 1.8 meters in air. So the spot size is big. So to improve the lateral field penumbra, there is this last element of the beam line that is an MLC. So we have 5 leaves in each side and 2 jaws, so 4 jaws in total. And they collimate layer by layer the field. And this is important for the out-of-field considerations, that we trim at most half of the spot. So the rule is that the centroid of a spot cannot be placed on top of any collimating element. So at most, we trim half a spot of the outer contour of the field. And the speed is 1.2 seconds per spot, and the design has been optimized to prevent leakage between leaves. And let's see if it works. I have a video. Doesn't work now? I had a video to show you the moving of the leaves. Yes, now. So here you can see how they move. So this is if we were seeing from inside the machine. So they move very fast, and they follow the outer contour of the field, and they do this layer by layer. So energy layer by energy layer. Yeah. So this is also something important to consider. So which is the effect of the position of the energy selection system. In our case, the energy selection system is in the nozzle. So we extract a beam of fixed energy, so the pristine energy, and then we have the range modulation system, that it can either be a rotating wheel, like in the passive systems, or in our case, we have this insertable plate that move in and out, and then we generate all the possible energies. And one characteristic is that the width of the Bragg peak in depth is constant for all energies. And then the other option, that is, for example, the accelerator, the proton accelerator in Trent or in Krakow, is of this type. So there is the cyclotron, then there is the degrader and the energy selection. And then there is the transport, the beam transport line that brings the beam to the different treatment room. So the energy selection system is upstream. And as a consequence, they have different energy spread. And what we also see when we perform depth dose measurement is that the width of the Bragg peak in depth is smaller as we go down with energy. And here is, I just summarize a little bit some of the differences that might be relevant for the talk of today of our machine and the IBA Proteus Plus, that's the one in Trento, which is similar to the IBA Proteus C235 in Krakow. So the cyclotron type in Maastricht is synchronous, and the IBA is isochronous. And we have a superconducting system, and the other is a normal conducting. And this is also important, especially for the talk of Gabriel. So the temporal beam structure for our beam is a pulse beam at 750 Hz, and we have a pulse width of 10 microseconds. And the other beam in the other facilities is continuous. Regarding the maximum energies, we can cover is the same. We can cover the same depth in water. And regarding the minimum energy, so as I said, we can cover from the surface, and the minimum energy of the other system is about 70 MeV, which means a range in water of 3.5 to 4 centimeters. So in order to treat shallow tumors, these systems also need a range shifter. And the energy change, in our case, is a range modulation system that is in the nozzle, close to the patient. And for the other systems, the energy selection system is upstream with a multi-wedge degrader that is immediately after the beam extraction. And we have a multi-leaf collimator of aperture, and the other systems don't. So that's my last slide, and I would like to thank again Work Group 9 and Work Group 11 of EURADOS for coming this long weekend in October 2019. And thank you for your attention.
Thank you, Gloria. That was a very clear presentation, and thank you for introducing us to the Mevion system. And if you have any questions to Gloria, please feel free to write it in a chat. So our next speaker will be Gabriele. Gabriele is right now working in the ELSE Nuclear in Italy, but he did his PhD in Politecnico in Milano, which was followed by the postdoc in CERN in Radio Protection Group. And from 2017, he was working in Working Group 11, where he's focusing on high energy pulsed field dosimetry. So Gabriele, feel free to start your presentation.
Okay, here we are. So, yeah, I think that it's working, I guess. So, good afternoon, everybody. I'm Gabriele from ELSE Nuclear. I'm here to discuss the experiment we performed with active detectors in the Mevion field. And I will show you which were the challenges we found and the findings we got at the end. First of all, I would like to thank all the team and the institution who allows us to perform our experiment, in particular from Maastricht, for the support during and also after the experiment. I will give you just a general overview about our experiment. Then I put some reference all around my presentation, so you can go and explore by yourself in several articles all the details. I will just introduce some concept which will be useful to understand what we did and why. Then I will talk about the experiment and at the end, eventually, the comparison with other experiments, both from EURADOS or from the general literature. Gloria already showed you which are the main characteristics of the Mevion accelerator. And from the active detector point of view, the main feature are that the energy selection system is really close to the patient, because actually also the accelerator is basically mounted on the gantry. And the second thing, which is really important, is that the beam is pulsed. Talking about pulse fields, we have just to see what happens from a detector point of view. Which means which is the time structure of the beam. So on the left, there is a sketch of what you should expect with a steady state field, in which you have a certain machine current. And of course, the stray beam will follow the same time structure. So we measure a dose, total dose, or a dose rate in this case, and we can compare it with the saturation level of our detector, which is always declared by the vendor. And we know just by measuring if our instrument is working or not. What happens in a pulse field is that the pulse is really short, of the order of microsecond or less, and the frequency is quite low. So what does it mean? This means that when you are measuring, most of the time the beam is off. And if the average dose rate is the same, this means that within a single pass, the dose rate or the total dose is really high, and this means that your detector might saturate. The problem is that if we measure a dose rate with a standard detector, we can compare if we are in a steady state field, but in the case of a pulsed beam, we cannot really measure the dose rate within the single pulse. Just a few words about RAM counters. Probably all of you know, but just to give you an overview. A REM counter is basically made of a thermal neutron counter placed inside a moderator or a moderating structure, which is functional to the response in the sense that the final response function of the overall instrument is designed in such a way that it follows the H*10 coefficients, which means that we have just a single conversion coefficient in between the counts we are getting from the thermal neutron counter and actually the dose. There are basically two families of REM counters, the conventional ones, which basically work up to 20 MeV neutrons, and the extended range one, which can cope with neutrons up to, let's say, GeV energy or so. How a REM counter behaves in a pulse field? Actually, it's a particular behavior because we are using a thermal neutron counter inside the moderator. So neutrons arrive to the detector, but then have to thermalize and drift and then reach the detector. So even if our primary pulse is of the order of microsecond or picosecond, for instance, in reality, what we see at the detector level is a spreading time, which lasts for several hundreds of microseconds. So in terms of capability of counting this signal, what happens is that independently of the pulse width or the, okay, if it's a pulse, so if it's short enough, with respect to this 100 microsecond behavior, what matters is really how much dose we deliver within the pulse, so not the duration and not the dose rate within the pulse. So what happens is that the higher the dose per pulse, the higher the amount of neutrons we can lose because we are above our detector saturation. So for certain dose per pulses, maybe we can count even if our detector is not designed for pulse fields. But if the dose per pulse is too high, maybe we will saturate. So coming back to proton therapy, why using or not REM counters? Well, of course, we have several pros in the sense that actually we have a direct measurement of the H*10, so we don't need to perform spectrometry or so. They are insensitive to gamma rays, and there's a long tradition of usage. Some cons, of course, we have to select properly depending first on the energy response of the instrument. So if we are expecting an high energy beam, then we have to go to extended range REM counters. And we have to take care about the pulsed or not structure of the beam, because we can correct for sure if the beam is steady state, so there are correction models. There are also other correction models to correct our response if the beam is pulsed, but the problem is that these models are based on the dose per pulse, which usually we don't know. This is just a sketch to show you, this is taken from the literature, and you can see that we are plotting the reference dose per pulse and the measured one, and depending on the instrument, they are all REM counters, the response of the device is really different depending basically on the electronics. So let's go back now to our experiment. The experiment was performed using 9 different types of REM counters. They were placed around a water tank phantom at 9 defined position. Then we move the detector from one position to the other, and we repeated the same treatment. So what we have at the end are 81 comparison points. So one measurement per position per detector. This is basically the map. So we measure around, let's say, 2 meters from the cubic treatment. The measurement was performed downstream of the interaction point, but also on the back, so all around. And we test several REM counters, as I told you before, both conventional and extended range. We have here the problem that since the beam is pulsed, we need a reference instrument that can cope in principle with pulse fields. And basing from some literature studies, we selected the Lupin, which is an extended range device, so it can cope up to GeV, but it's also specifically conceived to withstand pulse fields. So let's briefly go to the results. On the left, I plotted the dose we measure normalized to the treatment gray as a function of the different position. And what we can see from this left plot is that almost all REM counters measure more or less the same dose, but with the exception of the Lupin, which in all cases measure significantly a different value from all other detectors. So if we assume that the Lupin is working properly, then we can plot the same data in another way. In this case, I plotted the underestimation, assuming that Lupin is working properly, of all REM counters as a function of the measured dose from the Lupin. So what we see here is that the higher the dose, as this the beam structure was always the same, the higher the dose per pulse, it seems that the higher is the underestimation of all detectors, and then depending on the type, we have a different response. The interesting thing is that we don't see really a difference in between conventional and extended range. For example, the Linus, which is an extended range REM counter, underestimates quite a lot with respect to the Lupin. Now, just to have some more detailed data analysis, what we did was to take the measurement from the Lupin, which was discretized in time, and combine it with some further information, in particular the machine log files. And since we also used conventional REM counters, we need to introduce also some spectrometric information, because if we are above 20 MeV, then the response is different. So by combining all this information, we can plot some scatter plot like this one, which compare the theoretical underestimation based on all this information and literature data, and actually what we measure. And what you can see is that more or less in all cases we were able to predict and reconstruct which should be, and actually it was like this, the underestimation of the detectors with respect to the Lupin. So this means that actually the Lupin was correctly measuring the dose delivered, even if it was delivered within pulses. So using the Lupin data, what we can see is that our average dose rate at a couple of meters from the treatment point was of the order of 100, 200 microsievert per gray. And the higher dose was on the back, so not downstream as we can expect, but on the back, so close to the range modulator system, basically. How to interpret this data? We can compare with past experiments, basically from other EURADOS experiments or from the literature. And what we can see is that we have two big families of systems, some which are in which the selection of the primary energy is active or far from the beam, in which the average dose at the same position for similar treatment plans is 1/10 of what we were measuring at Mastro. Conversely, with the other passive system, actually, the dose was really similar, but with another difference, which is, in that case, the highest dose was downstream of the phantom, so we have a huge contribution also from internal neutrons, but in our case, the dominant part were external neutrons, also because actually the energy selection is really close to the patient. If we want to extend our view to other type of machine, here I plotted, these are basically literature data comparing passive system and active system at different energy. And actually what we can see is that Mevion is in line with other passive facilities. The dependency, depending on the treatment plan or the energy, is still present, but the main difference is made from active system and passive system. So we have this one order of magnitude difference in the average, let's say, dose per treatment gray. Concerning conventional radiation therapy, so photon therapy, here from the neutron stray dose point of view, we don't see much differences. Of course, if we are focusing on high energy conventional radiation therapy. And in this case, most of the huge difference is not made from the neutron point of view, but mostly from the out-of-field dose due to photons in this case. So just concluding, the Mevion machine is really interesting. It's really particular because it combines passive energy degradation really close to the patient, and it's extremely compact. Another feature is that the beam is not continuous in time, but it's pulsed. So this results in a pulsed stray neutron fields. In terms of neutron H*10, actually the Mevion is in line with other kind of passive systems. And in this case, we saw that most of the dose was not due to internal neutrons, so neutrons produced in the patient himself, but produced in the machine. Concerning the dose per pulse, the dose per pulse in this case is quite high if we measure quite close to the patient. So it is important to select proper instrumentation, so either passive detectors, or if we focus on active instrumentation, we have to select REM counters specifically conceived to cope with pulse field. Because we saw that the underestimation was of the order of a factor of 2 or even more. So that's all from my side. And if you have questions, please feel free to write it in the chat.
Thank you, Gabriela. It was a very nice presentation. I really like it because it always feels complicated to understand the pulsed fields, but you've made it in a very clear way. So thank you again. And our next speaker is Maria Davidkova from National Protection Institute in Prague in Czech Republic. Maria is an expert in dosimetry and radiobiology. And today she will talk about the second part of the experiment performed in Maastricht, so in phantom measurements using passive detectors. Maria, can you share your presentation?
Yes. Coming. I hope you can see it now.
Yes, but not in a presentation mode.
Let's make it better. Okay. Good afternoon, everybody. I am presenting the results of measurements with passive detectors on behalf of a number of laboratories and researchers participating in Working Group 9, Radiation Dosimetry and Radiotherapy. So the objective of the experimental campaign was to characterize secondary radiation field and compare it with the previous experimental campaigns. So our experiments and measurements at Mevion facility was using the same techniques, detectors and phantoms as in previous experiments, so that we can really compare out-of-field doses. And the first experimental part was dedicated to 3D mapping of out-of-field doses in water tank phantom. And the second part was a determination of organ doses during the treatment of brain tumor in anthropomorphic phantoms. And we were using two phantoms, 5 and 10 years old children. So first, I will focus to water tank experiments. As I said, we used a water tank phantom, which was developed previously, and detectors are placed using 5 frames. Within frames are fitting 5 pipes. You can see the schematical representation of water phantom, and detectors are placed at the exact positions at the distances from the beam direction and from the isocenter. We were irradiating the same target volume of 10 centimeters, the cube of 10 centimeters, with the different doses of 10 to 40 grays, depending on what type of detectors was placed in the pipes in water. Related to their sensitivity. So here on the next slide, you can see the more detailed picture of pipes with included detectors And here in the center down, you can see exactly the spaces where detectors were placed. We were working with thermoluminescent detectors of different composition with different content of lithium fluoride. Lithium 7 and lithium 6 have different sensitivities to photons and neutrons. And as you will see further, we can use the difference of response of these detectors also to estimate doses from neutrons. Except thermoluminescent detectors, we are working with radiophotoluminescent detectors and track edge detectors from basically 2 laboratories with very different methodology for analysis. The detectors can be seen also here on the small photos on the slide. So to the results, here you see the representation and comparison of photon doses measured as a function of distance from the isocenter. So here maybe the small picture is good to show the position of pipe 1, which is below the target volume, and frames in positions in different frames. So these are different distances along the beam, and the values in the table are a comparison of previous experiment in Trento, where no range modulator was used, with Mastro, where range modulator and passive elements are present. The difference of photon doses is about twice as higher in Mastro in comparison to Trento. When we look neutron dose equivalents, which are measured by track detectors, here you see different representation. One frame, the middle frame 3, was selected, and you see different pipes from the bottom to the top. And both laboratories, University of Barcelona and Nuclear Physics Institute in Prague, and you again the neutron dose equivalents are represented as a function of distance from the isocenter. In gray, here you see the target volume irradiated with the maximal dose, and then the decreasing neutron dose equivalence as a function of distance. And I would like to mention very good agreement of results from both laboratories. When we look, when we put these values again in the table, we can again compare really 3D distribution of neutron dose equivalent at different positions in water phantom for irradiation where no range modulator has been used, and for Mastro with range modulator and passive elements. And the difference between the doses, in this case, neutron dose equivalence is again about twice. The values for Mastro are higher, about twice in comparison to Trento. The second part of the lecture is dedicated to measurements with pediatric anthropomorph phantoms. These phantoms are Circe phantoms. You can see them on the picture as they are complete. They are composed of layers. Maybe on the head are better seen. In each layer and in the phantom, the tissues are represented by different materials, and there are small holes where passive detectors can fit. On the slide in the center, you can see the place where target volume representing irradiation of brain tumor was placed for both 5 and 10 years phantoms. So the treatment plan was very similar for both phantoms. And we also studied clinical treatment plan for head and neck of 10-year phantom, which are composed of 7 fields. And here you can see a representation or already complete phantom containing detectors just before irradiation. The same types of detectors were used for both 5 and 10 years phantoms. For 5-year phantom, there are special developed inserts which allow insertion of bubble detectors and track detectors from University of Barcelona, which have bigger size and do not fit in the Sears phantoms. So we have results for these detectors only for 5-year phantom, but you will see them also in the next slide presenting results. When we look already for the results on photon doses, we represent also doses divided by dose to the target. In order to be able to compare different experimental arrangements and treatment plans. You see that for 5 and 10-year phantom, photon doses are very similar and decreasing as a distance from the isocenter without much difference. The same thing is valid also for neutron dose equivalent for the brain tumor treatment. And here, except the results for trackage detectors, you see also gamma equivalent neutron dose, which was determined as a difference of results measured by thermoluminescent detectors MTS 6 and 7. When we compare now neutron dose equivalence as a function of distance from the isocenter in the pediatric phantom for different installations, here you see the results for Mevion. Squares and full triangles are results for range modulator measured at Mevion facility. And these results are compared to irradiation with no range modulation in Trento and range shifter and beam compensator in Krakow. You see that for Mevion, the neutron dose equivalents are quite, the slopes remains quite constant. And up to 25 centimeters, these installations or the techniques of irradiation of brain tumor are very similar. Only for larger distances, the range shifter and beam compensator deliver the lower neutron dose equivalence. These values, which are well represented as a function of distance, we can use for calculating organ doses when we take detectors in particular organs and we make average. So here on next slides, you will see these results as organ doses. So photon doses for brain tumor treatment are compared here for both phantoms for 5 and 10-year phantom. And you see that for phantom representing smaller child, organ doses are slightly higher because the distances of organs are smaller from the target volume. The same property can be seen also for neutron dose equivalence calculated in different organs, except the results for 5 and 10-year brain irradiation. You see here also results for head and neck clinical treatment plan. I would recall that this was irradiation from 7 fields in comparison to brain irradiation composed by 2 fields. And again, the doses for smaller phantom are higher than in a 5-year phantom than in 10-year phantom. But for head and neck treatment, we have mainly for organs farther from head, we have higher neutron dose equivalent, significantly higher values, but this corresponds again to the distance from the target, from the irradiated target volume. When we compare doses from photon and neutrons, so basically this is a summary of previous slides. So here you see in blue values for photon doses, and gray histograms are representing neutron dose equivalents. You see that for neutrons, we have higher values, that it's about order of magnitude higher, especially in the organs which are farther from the target. And when we compare organ doses to different proton beam treatments, so when we compare Mevion measurements, these are range modulator, represented as range modulator set. When we compare the results to no range modulator or irradiation using range shifter or beam compensator, so you see that for thyroid the treatments are very comparable, but for farther distances, range modulator, the non-neutron out-of-field organ doses are higher. The same representation is here shown for a neutron dose equivalent. Both slides corresponds to the brain tumor treatment. So this corresponds to the fact that we irradiate a shallowly located tumor, and the proton range should be somehow arranged to the target volume. So in this case, for neutron dose equivalent, again, you can see here comparison of range modulator with range shifter and beam compensator treatment. And you see that for organs, thyroid, lungs, up to breast, all proton beams treatments are comparable, and only for liver and stomach, for some further organs, is the irradiation at Mevion produces a little bit very slowly higher neutron dose equivalents. The last set of data corresponds to double scattered passive beam. These data are not measured but calculated by Monte Carlo, and you see that for passive scattered beam, the doses are even higher than for range modulator. And when we compare brain tumor irradiation and head and neck, and we put all results together, so again, photon doses are shown here in blue, and neutron dose equivalents in gray. So you see that for organs which are very close to the target volume, the photon and neutron doses are similar. And just for the higher distances, the neutron dose equivalent are higher than photons. So in summary, we could measure using passive detectors out-of-field doses in a water tank phantom and organ doses during treatment of brain tumor in pediatric anthropomorphic phantoms. And our main conclusion is that organ doses to normal tissues during irradiation of shallowly located brain tumors in pediatric anthropomorphic phantoms are comparable to proton treatments applying range shifter or 3D printed compensators. So with that, I would like to thank you for your attention.
Thank you, Maria, for the very nice presentation. I guess it was not easy to gather data from the hundreds of detectors that you had. So thank you again for sharing your data with us. And our next speaker is Carlos Domingo from University Autónoma de Barcelona. Carlos has a long experience in measurements in radio protection, and he's our expert in spectrometry. And today he will show the third part of the experiment, so the spectra that were measured around the phantoms at Mastro Clinic. Carlos, please share your presentation.
Thank you very much. I'm trying to share the presentation if I am able to do that. Okay, you should see it right now. Is it so? Yeah. Okay. So I am going to give an overview of the results of neutron spectrometry. Unfortunately, in the time of the talk, I cannot present everything, all the specific problems that we had to solve. Some of them were already explained by Gabriele. I mean, it's the same type of problems with pulsed field measurements. So, okay, so let's go ahead with the experiment and the results. So in the talk, I will first give an overview of the radiation. So for that, the talk from Gloria has helped me a lot, and I will have not to explain a lot of things. I will give an overview of the three binary sphere systems that we used for spectral measurements. I will also give an overview of the simulation that we perform, and then we'll go to the results, the spectra, integral quantities, some discussion of the results, and to finalize with some concluding remarks. So here I have not to explain a lot of things. Gloria has already explained the characteristics of the accelerator of the Mevion Hyperscan system, so I'm not going to tell anything else here. Here I am going to say something about the radiation that we did. So we have here the map of points which we intended to characterize, to make the spectrometry in these points. In principle, the detectors, the binary spheres from IMGU were intended to measure in points 5, 6, 11, and 14, UAV 1 and 3, and MPL 12 and 13. So we radiated the 10-year-old Cirrus Phantom with single energy protons, 122 MeV. Okay, so here we have the characteristics of the radiation, and I have to emphasize here that this is not a clinical treatment. We couldn't go for a clinical treatment because we wanted to reduce the charge delivered by the accelerator per spot, per pulse. This is in principle to avoid as much as possible the problems that Gabriele was talking for the pulsed field. So not having a high charge or a high dose in every spot. So the problem is that in order to do that, the accelerator could not work in the same mode as for treatments. So had to work manually, and this meant that we could not make the spread out Bragg peak with different energies to simulate a real treatment. So we were treating a single layer. Okay, so that's the time structure of the beam, as it has already been said. The points are the same points of measurement than for the REM counters, and the same points or very similar points to some former experiments with it. Okay. Then we go to the three extended range Bonner sphere spectrometers that we used. These three Bonner sphere spectrometers were checked not in this experiment, but before. They were checked to be compatible. They gave the same results, even if they use different detectors and different unfolding methods. But in former experiments, we did measurements at exactly the same place under the same conditions, and the results were completely compatible. So this is why we used the spectrometers in different points, because we know that without moving the spectrometers from one point to the other, all the spectrometers will give compatible results. So I am not going to go into many details. In the UAB spectrometer, total of 15 configurations could be used, including the high energy ones with metal inserts in the spheres. In this case, we use an helium-3 field proportional counter, and we use the fluid unfolding code. For the Helmholtz center Bonner sphere spectrometer, this is a spectrometer based on a proportional counter helium-3 as well, SP9 from Centronics. Again, 15 different configurations plus 15 polyethylene spheres configuration plus spheres also with metal inserts, with an electronic system with pile-up resection and dead time correction. In this case, unfolding was performed with the MSAN-B unfolding code. And finally, the MPL system is also a system based in the SP9 helium-3 proportional counter, also with the spheres, a number of spheres with also metal inserts. And here the data acquisition is done with a KN dual digital multi-channel analyzer, and the unfolding is done with the Maxed code. So these are the spectrometers used. And also I am going to talk about a few things about the simulation that we did. I have to say that the aim of the simulation was not to get, very exact results of what we expect, was only to produce gas spectra for the unfolding to be, to start the unfolding. So simulation was done with MCMP version 6.2, and the characteristics of the beam are given here. We are not simulating the accelerator. We are simulating only the proton beam, okay? The primary proton beam given by the accelerator at 227 MeV. Then we include in the simulation the neutron-producing components of the accelerator. That means the scrapper, the beam scanning magnet, the energy degrader, which converts the 227 MeV protons to the 122 MeV protons that we have used in the radiation. Also, the adaptive aperture is put in the simulation, and the room walls are also included in the simulation. The irradiated, I mean, we have put a voxelized phantom of the 5-year-old phantom of the 5-year-old child for the simulation. This is because this was the phantom that we had available. I mean, we had available this voxelized factor phantom. We don't have the 10-year-old phantom available voxelized. I mean, as the reason to have the simulation was to have the gas spectrum from unfolding, we thought that the main characteristics of the spectrum will not be very different if we put the 5-year-old or the 10-year-old. Okay, the amount of neutrons produced will be probably different, but I mean, being just the gas spectra, then the unfolding procedure is able to scale the results with respect to the simulation. So these are the results of the simulation. So I'm not going into much detail here, but only to tell that, of course, you see the high energy peak as more prominent when you are more in the forward direction, and then you lose this this high energy peak, you lose it in the different positions, right? So these are the results of the fluence from the simulation. This is the total fluence per gray, per treatment gray. And also we have the components of the different energy components of the spectrum, and also the percent of these components that we have. This is for fluence. And in this case, it is for H star for ambient dose equivalent, right? So, okay, these are the results from the simulation. And after that, we start to go to the results of the measurements. These are the graphs of the unfolded spectra in the points measure. I have to say that we were intending also to measure points 11 and 14, which are not here in the results, but there were problems in the data treatment because of high pile-up and dead time problems. So points 11 and 14, we cannot show the results because we were not able to get, I mean, measurements which were reliable. So in the other points, we didn't have this. Okay, no, I don't want to say we didn't have these problems. Yes, there were problems, but they could be corrected. They could be managed with, I mean, data treatment in these cases. So I'm not going into the detail of the data treatment, but because it will take too long to explain. So here we have the unfolded spectrum, so the result of the measurements compared to the spectra obtained from simulation. And we see that from point to point, so there are points where more or less the form of the spectrum more or less agrees. In some of them, some neutrons are in the measurements. I mean, simulation was not perfect. There were not all the elements in the room. So that's the main reason why in some points the simulated and the unfolded spectra do not fit well, okay? But again, there were the gas spectra which were simulated, and then the unfolding gave the spectra which better fits the experimental counts from the detectors. So if we go into numbers, if we finally give a look at the numbers of the total dose equivalent, of the total ambient dose equivalent measured. So we have here the values obtained for the different points. Also with all the information about the fluences and the fraction of fluences and fraction of dose equivalent. I mean, I think it's worth to emphasize that the main component of the measured ambient dose equivalent comes from neutrons in the evaporation peak groups. That means between 100 keV and 20 MeV. Okay, some relevant contribution comes also from the high energy neutrons, but no relevant contribution to those comes from thermal and epithermal neutrons, right? As expected because of the fluence to ambient dose equivalent conversion coefficients. So if we compare these results with former experiments, in particular with that from Krakow, which was the experiment done without any range shifter, beam compensator, and so on, we see that in general, the results from the Mastro experiment are around 10 times higher than those measured in Krakow, which is also similar to what the REM counters found. I have also to say that if we compare the results from Mastro to results with range shifter and beam compensator, then the results are similar, or even Mastro is a little bit smaller, okay? And also comparing results from Mastro to results obtained in photon accelerators, the results are also similar, okay? So after that, the concluding remarks of the presentation or the results from the spectrometry is that we measure with 3 different binary sphere systems and using different methods which were previously checked to provide equivalent results. The pulsed structure of the beam was challenging for analyzing the results. We had to skip the measurements in 2 points because we couldn't correct from them. And also, there's not good agreement between Monte Carlo and measured values. One of the reasons is that the elements in the treatment room were missing in the Monte Carlo simulation. It was a simplified Monte Carlo simulation with the aim of providing gas spectra for unfolding. And then the H star values were about 10 times higher than those measured at Krakow, but it has to be taken into account first that treatments were not comparable. In Krakow, we perform a clinic treatment. Here we perform a treatment we perform a treatment with a fixed energy, which also makes the puts the question of if the reference dose is comparable in a clinical treatment and in a treatment where we only give one layer or we only give one energy. And also comparable, the results in MASTRO were comparable to values obtained using passive methods, range shifters, compensators, and so on. And finally, I have to say that all these results here are not my results. They are the results of the team who we are self-called the Bonner Spheres teams or the balls team. Okay, so thank you very much. So that's all from my part.
Thank you very much, Carlos. I have a quick question to your presentation. What was the agreement between the systems, different Bonner sphere systems?
That was checked. I don't remember in which of the experiments. I don't remember in which of the experiments that was checked. Probably in some of the experiments in Krakow. We put the three systems at the same point. And the results were completely inside the uncertainties for those equivalent values for the fluence values. And graphically, you say that the unfolded spectra were, compatible. I have to say here, I have to emphasize one thing. Sometimes putting a graph of the spectra is a little bit misleading because we are not representing the spectra, we are representing the spectra in a lethargy representation, which is quite good for some things, but you are not plotting the real spectra. You're plotting something related to the spectra. So eye comparison, sometimes you see things that by eye, they look different. But when you calculate the integral quantities and the distribution of the dose and of the fluence between the different energy groups, then you get the same. And this is what we got in the comparison. Okay, so.
Okay, thank you very much for your presentation, and thank you to all speakers for their presentations. I have a question to Gabriele about his results for pulsed fields. Gabriele, from your experience, which detector would be the best in case of flash? Because over there we have also very high dose rates, and also that could be a pulsed field.
Okay. So again, it really depends on which is the dose per pulse you are expecting, basically. So maybe from simulation or from passive systems, basically. What is really different might be the pulse duration, which is not an important quantity at the end. So what really matters is the dose per pulse. We are within EURADOS. I know that they are testing some devices in flash-like conditions for sure at CLEAR, for instance at CERN. And to my knowledge, they are testing some detectors from Berthold, some from Else, de Lupin, actually. But since the issue is the dose within the pulse, if you don't have a reasonable guess, in principle, you don't know. Of course, in principle, it's always better to use something which has the cleared range in terms of dose per pulse, so not dose rate. And otherwise, just go for passive detectors, and then you can move to active.
Yeah, thank you. That's passive, always a good safe solution.
Yeah.
Thank you very much. And Maria, I would like to ask you, based on the experience and measurements that you present, do you think that introducing, because there are more and more systems who are using some sort of beam modifiers like collimators or 3D printed modulators, do you think it will be a problem from the point of view of patient radioprotection, or we will be within the numbers that you showed us?
My personal opinion is that the results for proton beam modulation using all these techniques, the results will be quite similar. You see that really we compare the technologies which are very close to the patients, which are a little bit farther, and we are still within very reasonable values or results for both photon doses as well as neutron dose equivalents. We didn't speak and discuss much the comparison related to photon beams. Then the results would be very much different when we, or the difference between photon and proton beams, it's much larger than between different proton beam technologies.
Okay, thank you very much. I don't see other questions, so I would like to thank to all speakers again for their presentations, and also thank all participants who spent the afternoon today with us. And you are more than welcome to check EURADOS and contact us if you are interested in our research. We are very eager to collaborate with new members. Yeah, let's stay with touch with EURADOS. Thank you very much again. Bye-bye.